ME350 example problem for lump capacitance method for thermocouple analysis. A fine thermocouple with a spherical bead with a diameter of 0.025 millimeters is initially at a temperature of 20 degrees Celsius. The bead is then submerged in a liquid at a temperature of 70 degrees Celsius. The convection heat transfer coefficient is estimated to be 50 watts per meter squared Kelvin, which corresponds to forced convection with gases or natural convection with liquids. Determine the time until the bead temperature reaches 67.5 degrees Celsius. The thermal conductivity, density, and specific heat for a typical type T thermocouple at the average bead temperature are provided. Our first assumption for this problem is that the temperature within the bead is uniform at each instant in time. Use of this assumption is called the lumped capacitance method, and we will calculate the Biot number to ensure that this is a valid assumption. Our second assumption is constant properties, which is reasonable as long as the properties have less than a 10% variation over the range of conditions. Our third assumption is that there is negligible internal heat generation, which is reasonable for a thermocouple with very small currents. Our fourth assumption for this problem is negligible radiation for the exterior boundary. This is a reasonable assumption for an opaque wall and for moderate temperatures combined with significant convection at the exterior boundary. Our fifth assumption is negligible conduction through the lead wires for the thermocouple, which is reasonable since they are probably at a similar temperature as the bead. Our sixth assumption is that the thermocouple bead is perfectly spherical. This allows us to use the geometric equations for a sphere for our calculations. As indicated by our first assumption, our first task is to check the magnitude of the Biot number, which is a dimensionless parameter that compares the rate of convection at the surface of a body to the rate of conduction within the body. A Biot number less than 0.1 indicates that the body conducts heat well enough to be approximately at a uniform temperature throughout. Note that the characteristic length used for this calculation compares total volume of the body to the surface area for convection. For a perfect sphere, we get that this is 1/6 of the diameter. Plugging in values, we get a Biot number that is well below 0.1. Thus, using the lump capacitance method is valid. Before continuing, just for fun, we solve for the largest diameter for which the lump capacitance method would be valid. For these conditions, our bead can be up to 27.6 centimeters in diameter, which is quite a large bead. Now we are ready to begin our analysis by first applying conservation of energy to a control volume that contains the thermocouple bead. For this case, there is no energy leaving the control volume and negligible heat generation. Thus, neglecting radiation and conduction in the leads, there is just a balance between thermal energy going into the bead by convection and the rate at which sensible energy stored within the bead is increasing. Note, this equation is an ordinary differential equation because the temperature only depends on time. Next, we substitute theta in for the temperature difference and define tau as shown. Separating variables, we integrate this equation from our initial time to the final time. Finally, we solve for an equation for the final time. Substituting in values, we first calculate a value of tau of 2.84 seconds. Note this quantity represents a time constant for our process, which we will consider further on the next slide. Then we calculate the final temperature difference compared to the initial temperature difference is 5%, where the fluid temperature is used as the reference temperature. Finally, we get that it takes 8.55 seconds, or approximately 3 time constants, to reach this temperature. To consider these results further, I have used our earlier results to solve for bead temperature as a function of time and used it to make the plot shown. Looking at the figure, we see that the bead temperature asymptotes exponentially toward the fluid temperature with time. Also, note that tau, which has units of time, represents a time constant for the process. After one time constant, the change in temperature will be 63.2%. After 3 time constants, the change in temperature will be 95.0%, which corresponds to this problem. And after 5 time constants, the change in temperature will be 99.3%. Thus, to get a steady state temperature reading, you should wait at least 5 time constants for the bead to come into equilibrium with the surrounding fluid.